Chapter 14 is about acids and bases, and we're just going to do the part that pertains to our lab today, and we'll finish up the rest of that next week. Acids and bases undergo neutralization reactions. We are starting it right now.
But, I mean, did we start? Because I see it's 14.5. Only doing the section then?
We're doing 14.5 and 14.6, and then we're going to come back to the rest of it later, so that we have time for lab today. So acids and bases undergo neutralization reactions, and we've talked about these before. They are a subgroup of double replacement reactions, and the products are generally water and salt. Remember that when a chemist says salt, they mean an ionic compound, not necessarily table salt. So this reaction is an example. Hydrochloric acid and potassium hydroxide react to form water and salt. If we do the net ionic equation for that, we end up with hydrogen ion plus hydroxide ion forming water. And that is the net ionic equation for many, not all, neutralization reactions. Here's an example of one that has a different net ionic equation. If we mix hydrochloric acid with sodium bicarbonate, which is baking soda, we get a lot of fizzing. This is the same thing that would happen if you mix vinegar and baking soda. It fizzes and bubbles, right? That's because it's generating carbon dioxide. So there are neutralization reactions that also form carbon dioxide. They usually involve either a carbonate, which is CO3, or bicarbonate, which is HCO3, also called hydrogen carbonate. And the products are going to be gaseous carbon dioxide and a salt. And this is also called a gas evolution reaction because it gives off a gas. So what we need to know how to do, and we've done these before, is how to write a molecular equation for a reaction between an acid and a base. So here the acid is H3PO4, and here the base is sodium hydroxide. So the first thing we do is get the iPad to cooperate. The first thing we do is we write down the formulas for the reactants. We've got H3PO4, and we've got sodium hydroxide. Neutralization reactions can be treated as double replacement reactions because really that's what they are. In a double replacement reaction, we would take each of the reactants and break it into the ions. Do you remember this? And we would write the ions with their charges underneath. So what two ions are present in H3PO4? Hydrogen and phosphate. Hydrogen ion always H plus, phosphate PO4 3 minus. What are the two ions in sodium hydroxide? Sodium with what charge? +1. And hydroxide, right? -1. We need this periodic table done, don't we? Can't do chemistry without a periodic table. So, in chemistry land, we talked about this would be the guy and the girl, and they came to the party together, and these two came together, and while they're at the party mingling, they swapped partners. So sodium's going to leave with phosphate, and hydrogen's going to leave with hydroxide. So in the products, we just write them with their new partners. Always the positive ion first, and then the negative ion. Very important to have the charges there as well. So we look at H plus and OH minus, the same charges. If we just put those together, we get HOH, and that looks kind of funny, doesn't it? That's H2O. So that's H2O. And then looking at Na plus and PO4 3 minus, we need to put the ions together in a way that their charges add up to 0. One of the techniques we used was a crisscross. So 3 becomes a subscript for the sodium. We end up with Na3PO4. And if you have forgotten all of this, the final is coming. Next thing we need to do is balance the equation. Is it balanced as it is? No. What's one element that is not balanced? Sodium. On the left we have 1 sodium, on the right we have 3. So if we put a 3 in front of the sodium hydroxide, that will balance the sodium ions. What else is out of whack? OH. So OH is here and it's hiding in the water. So that gets a little trickier. So let's maybe think about all of, you want to look at the hydrogens or the oxygens? Let's look at the hydrogens. So here we have 3 hydrogens, and in this we also have 3. So a total of 6 H's on the left. And on the right, there's no hydrogens here, and how many hydrogens there? 2. So that means we have to write a 3 in front of that so that we get 6 hydrogens on each side. Now, if everything went okay, the oxygens should have taken care of themselves. Over here we've got 4 oxygens from the phosphate and 3 oxygens, so 4 plus 3 is 7. Here on this side we have 3 water molecules, is 3 oxygens, and 4 from the phosphate is also 7. So that's our balanced equation. Any questions? That should be reviewed. There are some other acid reactions that occur. Acids react with a lot of metals. Acid reacts with magnesium. We've done that in lab. We reacted magnesium with hydrochloric acid and it generated hydrogen gas, and then we did stuff with the gas. Remember that? And it also forms a salt. Sulfuric acid will react with zinc to form hydrogen gas and salt. Hydrochloric acid reacts with the metal iron to form hydrogen gas and salt. So there's a pattern here, right? Acid plus metal gives hydrogen gas and salt. There are some metals that do not react with acids. You are not responsible for knowing which of them don't react or do react. So if I ask you to write the products or write an equation for the reaction between an acid and a metal, you put them together so you get hydrogen gas and salt. What's happening here is that the acid is converting the metal to an ion. So this can be looked at as a single replacement reaction, where the chlorine and the magnesium, no, that doesn't work, does it? The magnesium and the hydrogen are switching places, that's it. I don't know where my brain went. It's also a type of oxidation reduction reaction. The magnesium, this is a picture, and we saw this happen. When you react the magnesium, you get a lot of bubbling, and that's the hydrogen gas. And when you're done, it looks like the magnesium disappeared. But did it vanish? No, it's still there. But now it's in an ionic form that is soluble. Another type of acid reaction is where an acid reacts with a metal oxide. So HCl reacting with potassium oxide will also form water and salt. Hydrogen bromide or hydrobromic acid with magnesium oxide, water and salt. So that's another pattern to be aware of. So let's practice these. The reaction of hydrochloric acid with strontium metal. We're supposed to write an equation. What's the formula for hydrochloric acid? HCl. And what's the formula for strontium metal? Just Sr. It's a metal, it's just the element, Sr. So these are going to react, and what did the pattern tell us they will produce? Hydrogen gas and salt. So we're going to get hydrogen gas, H2, and so that's where the H's go. And what we've got left is chloride ion and strontium as an ion. So I'm going to make a little note down here. I've got chloride ion and strontium. What charge does strontium take as an ion? 2 plus, right? Because it's in group 2. We know the formula by looking at their charges. It must be SrCl2. Because I need 2 of these chlorides to balance the charge on 1 strontium ion. What else do we need to do before we're finished? Balance the equation. So over here I've got 2 chlorines, and over here I only have 1. So if I put a 2 out there, that takes care of my chlorines. Strontium's okay, 1 and 1. Hydrogens, 2 hydrogens here and 2 hydrogens there. So we're all good. Any questions? Let's do part B. The reaction of hydroiodic acid with barium oxide. What's the formula for hydroiodic acid? What 2 elements does it have in it for sure? Hydrogen and iodine, right? Because we see this hydro, well, we know that all acids start with hydrogen, and iodic comes from iodine. We learned there were 2 kinds of acids. There were the binary acids, which is just hydrogen and another element, and then there were the oxy acids that had like chlorate and perchlorate and stuff in them. The difference was in the name that the binary acid starts with hydro. So this is just H and I. It's like a big friendly hi, right? No? We know it's HI because the iodine has a -1 charge, the hydrogen has a +1 charge. So it's just one of each. It's just high. Barium oxide. Well, that's an ionic compound. We have to look at the charges on the ions before we can just write down the formula. What charge does oxide have? -2. We look at the periodic table. Here's oxygen. We go over to neon and we count backwards. -1, -2. How about barium? +2, because it's in group 2. So we got +2, -2. We just smash them together, and we get BaO. So here we have an acid and a metal oxide. What does this make? Water and salt. They all are making salt, aren't they? This one's making water and salt. So our first product will be water. And then for the salt, we've got barium that didn't go into the water, and we've got iodide. See, the H from the acid and the O from the metal oxide got together to make the water. And here, the barium didn't go anywhere and the iodide didn't go anywhere, so they end up together. +2, -1. So this must be BaI2. Is it balanced? No. What do we need to do to fix it? We need to put a 2 in front of the HI. So we've got 2 H's. That takes care of our H problem, because here we've got 2 H's. Now we also have 2 I's, and in this formula we have 2 I's, and we've got 1 barium, 1 oxygen, 1 oxygen. The most important reaction that bases undergo is neutralization, and we covered those when we were talking about acids just now. There's only one other kind, and we're just going to mention it because it's kind of interesting. Sodium hydroxide will react with aluminum and water and form alum. And aluminum is one of the very few metals that will actually dissolve in something like sodium hydroxide. Most metals will not. And this forms an ionic compound that doesn't follow the rules that we learned. So we're just going to say, oh, look, there he is. What's weird about it? How many ions are there? How many different ions? There's 3. There's sodium and aluminum and hydroxide. And I told you that in this class, it was always 2. 1 metal cation and 1 anion. So there he is. Those guys exist. Done talking about him.